Well, it is a lovely day to do some math. In the last lesson, we looked at several different types of algebraic functions, specifically linear functions, polynomial functions, rational functions, root functions, etc. Today we're going to look at several types of functions that aren't algebraic, meaning we cannot make them with combinations of polynomials using addition, subtraction, multiplication, division, and exponents and roots. So the first family of functions that falls under this category of transcendental functions are the trigonometric functions. Now, trigonometry is such a rich subject that there's an entire course devoted to it. So of course, there's no way we're going to get through everything in 15 minutes, even an hour, even if we had a whole week. The hope here is that you have seen these trigonometric functions before, and their identities, and their graphs, and you've worked with trigonometric equations, and you've done all of that. And so we're just doing a very brief review here. So the first trigonometric function that everyone learns is the sine function. And here we have a graph of sine of x. The trigonometric functions are periodic functions, meaning they repeat again and again and again. When we look at the sine function, we note that the period is 2 pi, meaning every time we move a distance of 2 pi to the right, we start over and we have the graph again. And because the graph repeats, this actually gives us an algebraic relationship. If we take sine of x plus 2 pi, that's just equal to sine of x. Meaning if we evaluate sine 2 pi further than we started, we end up getting the same thing. Basically, if we shift this 2 pi units to the left or to the right, we end up getting the same graph, which is really interesting. Another thing we can note about the sine function is that it is an odd function. We can see it is symmetric about the origin. If we were to take this and flip it 180 degrees, we would get the same graph. And so because it's an odd function, that means that sine of the opposite of x is equal to the opposite of sine of x. So just by looking at the graph of this function, we can come out with a couple of identities involving the sine function. We note that the domain is all real numbers, which I'm going to write like this just to save space. This is a symbol that means all real numbers. And the range, if you look, is the closed interval from -1 to +1. Again, there's a lot more we could say about the sine function, but this is meant to be a very, very, very quick review. So that's all I want to say about it right now. Let's look at cosine. Here we have a graph of y equals cosine of x. It starts at 0, 1, and then goes down and up, again, in a periodic fashion. Every 2 pi, the graph repeats itself again. So again here, we can say the period is 2 pi. And so that means that cosine of x plus 2 pi is equal to cosine of x. If we evaluate cosine at some value, and then we evaluate it again 2 pi later, we end up getting the same quantity. This also means that if we shift the graph to the left or right 2 pi units, we end up getting the same graph again. If we look at symmetry properties here, we can see this is actually an even function, because if we flip this across the y-axis, we get the same graph. So that means we have an even function. And so that tells us that cosine of the opposite of x is just equal to cosine of x. And similarly, the domain and range is the same as sine. The domain is all real numbers, and the range is from -1 to 1 inclusive. Now, if we think about the sorts of things in the real world that might be modeled off of sine and cosine functions, some examples are tides and vibrating springs and sound waves. These are basically anything that is wave-shaped, is often related to a sine or a cosine. Now, I want to point out that these functions are not algebraic. They might kind of look like polynomials in that they're smooth curves that are going up and down, but because they change direction an infinite number of times, if they were polynomials, there would have to be an infinite number of terms. And in fact, there is a concept that you will see in Calc 2 where we can write these as the sum of an infinite number of terms. This might blow your mind just a little bit, but because we're here, you can write sine of x as x minus x cubed over 3 factorial. And if you don't know what factorial is, I'll tell you in a moment. Plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... going on forever. And a factorial, like 7 factorial, means we are multiplying all of the whole numbers from the number we started with all the way down to 1. So these denominators are getting larger very, 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 very quickly, which means that these terms, as we move from left to right, are in a sense getting smaller and smaller and smaller. I'm not going to talk about adding an infinite number of terms together right now because that is a little bit outside of the scope of what we're meant to look at here. But if you were to use a graphing calculator and you were to graph x, and then you were to add in this next term, minus x cubed over 3 factorial, and then add in the next one, and then add in the next one, you would see that the graphs that you get at each stage end up looking closer and closer like sine. Basically, every time we add an extra term, we get another one of these peaks and valleys. And as we keep doing that, the function looks more and more like sine of x. I encourage you to try it. It's actually a really neat thing to do. But for now, I want to look at one more trigonometric function. We know there are actually 6, sine, cosine, tangent, cotangent, secant, and cosecant, but sine, cosine, and tangent are generally the ones that we focus on the most. So let's look at tangent of x. And just to clean things up, I'm going to put some brackets in here so you can see which of these correspond to sine and cosine, and then whatever we end up doing down here will correspond with tangent. So we know that tangent x is sine of x over cosine of x. In fact, I'm going to write that here. Sine of x over cosine of x. And because tangent is a ratio, we know that if the denominator is 0, it's undefined. So everywhere cosine is 0, specifically the odd multiples of pi over 2, 3 pi over 2, etc., that's going to give us a 0 in the denominator, and tangent's going to be undefined. And specifically, we can see at these values, pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, we have vertical asymptotes, and that comes from the cosine in the denominator. Now, this is also a periodic function, as you can see, but the period isn't 2 pi. If you look at it, the period is just pi. Every time we move pi units to the right, we end up getting another branch of that graph. So it repeats every pi. That means that tangent of x plus pi is equal to tangent of x. We also note that this is an odd function. We can see that it's symmetric about the origin. And so because it's an odd function, that tells us tangent of the opposite of x is equal to the opposite of tangent of x. We also have 3 more trigonometric functions. I do not want to worry about their graphs right now, but I would feel bad not mentioning them. We have cotangent of x, which is defined to be the reciprocal of tangent of x. We have secant of x, which is the reciprocal of cosine of x. And we have cosecant of x, which is the reciprocal of sine of x. Again, my expectation / hope is that you have seen all of these before. You've taken a trigonometry class at some point. You are comfortable with these concepts. If not, if any of this is new and scary, you are almost certainly going to want to spend some time outside of class doing some trigonometry review on your own so you can get more familiar and more comfortable with trigonometric functions so that when we're using them in calculus, they are not something new and scary, they are something a little bit more familiar.